Today we're going to be looking at a short video on universal gravitation. So earlier in this course, we noted that gravity is easy to observe in our daily lives, and we experience the acceleration due to gravity as constant. It doesn't matter whether we drop a heavy thing or a light thing, any object that's dropped near the surface of the Earth accelerates downward at a constant rate. However, this cannot be true everywhere, because an object in space very far from the Earth would not accelerate down to the Earth as quickly as an object near the surface. Newton noticed this in the late 1600s and compared the acceleration of a dropped object near the Earth with the centripetal acceleration of the Moon, and noticed that the centripetal acceleration of the Moon was significantly lower than the acceleration of an object near the surface. He determined that the force between two-point objects was given by this expression, which is called the law of universal gravitation, where here F12 is the force on object 1 by object 2, which is equal to g, which is a gravitational constant, times the product of the masses, m1 times m2, divided by r squared, which is the square of the distance between them. And r12 hat in this case is a unit vector that points from object 1 to object 2. There's a couple of important things to notice about this expression. First of all, notice that it's always attractive. So it always points from object 1 to object 2. It's never a repulsive force, and it never acts in any other direction. It's always trying to attract the objects together. Another interesting point is that the force always exists. Notice that this denominator, even if r gets very, very, very large, the force has a very, very small magnitude, but it's never zero. So no matter how far apart two objects are, there always exists a gravitational force between them. In practice, this force is so small as to be not noticeable, so we typically tend to ignore it, but it's interesting that, unlike other forces, this force never actually goes away. Finally, notice that this force is symmetric. If we just took all of the 1s and 2s on the subscripts and swapped them, we would get the force on object 2 by object 1, and we would have exactly the same magnitude and the opposite direction, because r21 would point in the opposite direction of r12. Of course, we have to have this by Newton's third law, right? The force on one object by another has to create an equal and opposite reaction. So it's a nice check to make sure that it satisfies Newton's third law, but the formula automatically builds in this symmetry between the two objects. However, as I mentioned at the beginning of this video, we stated earlier in the course that every object accelerates downward with this constant acceleration g. How does this fit with universal gravitation, where clearly the magnitude of this force and therefore the magnitude of the acceleration depends on the changing distance between them? Well, the key is that for every height we can easily get to on Earth, the change in height compared to the surface is minuscule compared to the radius of the Earth. Thus, if we simply compare our two expressions, we get that little m times little g is equal to the net force, which is given by the law of gravitation. We can simplify this a little bit. We can call m1 simply the mass of an object, the familiar m in the mg formula. We replace m2 with the mass of the Earth, and then r is simply the radius of the Earth. So we get that little mg is equal to the gravitational constant times little m mass of the Earth over the radius squared. If we then cancel the little m's, we get that the value of the gravitational constant, our familiar 9.81 meters per second squared, is equal to the gravitational constant times the mass of the Earth divided by the radius squared. Just as a quick comparison, the radius of the Earth is about 6,000 kilometers. Cruising altitude in a plane is about 12 kilometers. If you plug this into the denominator, r squared, that's a change of 0.0004%. That is so small that the acceleration, even at the highest altitude that most humans ever reach, is still about g. So no matter what we do, as long as we're sufficiently close to the Earth that we can assume that r squared basically isn't changing, then this law of universal gravitation exactly explains this apparent constant g. That is not to say that it is constant. If you have careful measurements and very accurate measuring devices, you actually can measure the difference in the gravitational constant over a medium distance. Many of these experiments, for instance, have been done in mine shafts, comparing the value of the gravitational constant at the surface of the Earth to deep in the mine. But even then, again, these changes are, thousandths of a percent. So for all practical purposes, this gravitational constant is actually, the gravitational acceleration near the surface of the Earth is actually constant as long as we are not in a rocket flying away or close to the moon. That's all.